Okay, so someone was asking me about the relation between number of revolutions and delta theta. Okay, delta theta represents the total angle of rotation. And you know that a complete revolution corresponds to an angle of 2 pi. Okay, that's why if you know the total angle and you want to deduce the number of revolution, you just have to divide delta theta by the angle for one revolution, which is 2 pi. That's it. Okay? Okay. So let us continue
Okay, okay.
with problems. Another example. We have the 700 kilogram pipe is equally suspended from the two tines of the forklift. It is undergoing a swinging motion such that when the angle theta is 30 degrees, it is momentarily at rest. We want to determine the normal and frictional forces acting on the tine, which are needed to support the pipe at the instant theta is equal to 0. Measurements of the pipe and the suspender as are shown in the figure. Okay, so here we have a system. This system consists of a pipe, okay, that is attached by 2 rods, if you want, to O. Okay, now they told us that swinging is taking place from theta equals 30 degrees. يعني the initial angle is 30 and then we left the system. So if you want, we have this. This is the initial position. It was at rest and then we'll leave it. So when we leave it, it will undergo a rotational motion about point O. Now, since they didn't mention anything about the mass, if you want, of the rods, we can consider them to be negligible. So we have the main mass is in the pipe. We have a 700 kilogram pipe, which is can be modeled as a very thin disc. Okay, and whenever you have a thin disc, what is the inertia about G? So for a thin disk, the inertia about G is the total mass because all points are equidistant from G. So it's the mass of the pipe times the radius square. And the radius of the pipe square, please, here you should pay attention. There is 2 radius that we'll talk about. We'll talk about the radius of the pipe, which will allow us to calculate the inertia about G. But when we consider rotational motion, G is rotating about O, and the radius of rotation of G about O is equal to this distance, which is given to be 0.4. So we should pay attention in which case we need to use 0.4 and in which case we need to use 0.15. When we calculate inertia about G, we need the radius of the pipe. So we'll use 0.15. While when we do the analysis of motion, the system is rotating about O. So if you want to compute, and O is fixed, so we have rotation about fixed axis. So when we want to compute the kinetic energy, at the initial state, it's 0 because it's starting from rest. At the final state, it's equal to half inertia about O times omega final square, omega at state 2 square. Okay, and to find the inertia about O, all we have to do is to apply the parallel axis theorem between points G and O. So we already calculated IG. Now to calculate IO, here we need to use the distance of 0.4. So IO is IG plus mass of the pipe times the distance between O and G square. Okay. So this is how we calculate the expression of the kinetic energy. Now, the question is to find the normal and frictional forces acting on each of the tines, which are needed to support the pipe when theta equal to 0 degrees. Okay, so here, this is where we need to combine chapters, okay? Look, they ask for the forces at a particular position when theta is equal to 0. And when the system will come to this position, so this is the second position of the system. At this position, let us illustrate the forces. We have the weight of the system, and we have the reactions at O, okay, which can be divided into two components, normal and frictional forces. So we have, let's say, F, okay, and N. And here to calculate these forces acting on the system, okay, we need to apply kinetics, okay? So first, since we have circular motion, okay, the easiest system if you want to work with is normal tangential coordinates. So if I consider this is G of my system, I can draw UT UN vector. This is UT. This is UN. And I can apply that sum of T is equal to MAT. And sum of N, sum of normal forces, of course, AT of point G, okay? Always we take the acceleration of the center of mass. Sum of normal forces equals M times A normal at G. But can you tell me why I need the principle of work and energy here? How it will help me? How the principle of work and energy will help me? How you calculate your normal acceleration? What is the normal acceleration of G? You know that a G normal is Vg square over the radius of rotation. So over OG, okay? So to be able to compute the normal acceleration when theta equal to 0, you need to solve for the velocity of G at this instant. And the velocity of G at this instant is related to omega 2. So you can also say, you can replace Vg by omega times OG. So A normal is R omega square. It's OG times omega 2 square. So to be able to solve for sum of normal forces, you need to get your angular velocity from work and energy. Okay. So the first step then will be to apply work and energy to find omega 2. Then you go to your system. But here you have several unknowns. You have the friction, you have the normal, you have also still A tangential that is unknown. But A tangential of point G is alpha times R. It's alpha, which is the angular acceleration of the system, times the radius of rotation. Radius of rotation, which is here OG, okay? 0.4. Now, since if you want, you have several unknowns, F and alpha, you still need a third equation to close your system. And what will be the third equation? We have seen in kinetics, we have two force equations and one moment, or we can do more than one moment, as we mentioned before. So here's the easiest point. Yes. What is the easiest point to do moment about here?
Oh,
yes, about O, very good. So you can say since you have rotation about fixed.
لأن فيها أكتر شيء forces.
نعم, yes. So you can say sum of moment about O equals to IO times alpha. Okay. But if you look at the figure, what can you say about the forces doing moment about O? F and N are passing by O, no moment. The weight is also passing by O, no moment. So sum of moments about O at this instant, which is the vertical position, is 0. So at this position, we deduce that alpha is 0. And then, because alpha is 0, sum of tangential forces is equal to 0. So when you write sum of tangential forces, you only have the frictional force F. So no frictional force at this instant. You only have weight and normal, okay? And then you can say that the weight, if I consider here, let's say the normal to be up, okay? Because if you take the downward assumption, it will be wrong, and you will get a negative result since an is positive upward. So along un, what can we write? We have plus the normal minus the weight equals m or g omega 2 square. Okay, so to be able to calculate your normal, you need omega 2. That's why you need to apply principle of work and energy. So in this exercise, we have combined several chapters. We used chapter 17 and chapter 18. And this is the case in majority of problems. So always try to think in not in one chapter only to solve your problem. Okay, so let us now again develop the solution step by step. So first step is to apply work and energy, as we said, to calculate the final angular velocity. So since the pipe is originally at rest, the initial kinetic energy is 0. And we can write T2, you have two ways to do it. Or you do have inertia about O omega 2 square, as we did together, or you divide it into two components. You use the general equation, which is half mvg at state 2 square plus half ig omega 2 square. But as we know, vg can be related to omega 2 because of rotation. Velocity of g is the distance from O to g, 0.4 times omega 2. So this will allow you to get the kinetic energy at state 2 function of omega 2. Another approach is to say I have rotation about a fixed point, O, so I just have to apply half inertia about O, and I can get IO from parallel axis theorem, okay, times omega 2 square. You will get exactly the same result. Okay. Now, second step is to...
دكتور
Yes. Yes.
لو إذا كان عنا البايب كمان عم تبرم كان بيزيد شيء على الإيكويشن تبعنا تبع
Yes, of course. In this case,
total kinetic energy.
Of course. Then you don't have rotation about fixed axis, or you have general plane motion. So you have to consider the rotation about G plus half mvg square. Okay. And the rotation, total omega about G is summation of omega. Okay. So in this case, you need to consider, we'll go over such cases after. So if you have, you need to decompose, then into two components, as you said. So you can do half m times vg square. Okay. And the velocity of the center, you can still get it from the velocity of rotation about O times the radius. Okay. Plus, you need to add the rotational effect, half Ig omega square. And this omega here will represent the total angular velocity of the body, which is the combination of rotation about G and rotation about the axis of rotation.
Okay.
So now if we apply the work and energy principle, what is the only force doing work here in this case? We said that the frictional and normal forces are applied at the fixed point O, so no work. We only have the weight, okay? So you can say that I just have to compute the work of the weight. If we go back to the figure, okay, what is happening here, the system is moving downwards, it's rotating and G is moving down. Because G is moving down, then the work of weight will be positive. So we just have to compute the displacement, the vertical displacement of the weight. Since the weight is moving downward, this distance can be calculated by doing what? Who can tell me? How you find the distance traveled downward by G? I will do a figure for you to simplify things. This is your figure, okay?
R
Yes.
times
R.
theta.
No. أول شيء, look, G, if I take the datum here, okay? If I consider, let's say, this distance, this reference, I have, this distance is what? If the angle here is known, this is 30 degrees. Okay? At the initial position,
R cosine theta.
yes, this distance is 0.4 cosine 30. Okay? And now when I am at the vertical position, what will be the distance from this line? 0.4. So what is delta y? Delta y is the difference between these two. And it's negative because I take y positive upward. So delta y is minus 0.4 times 1 minus cosine 30. Okay? So I can say that the work of the weight is equal to minus mg, okay, times delta y, which is negative, times minus, okay, 0.4 times 1 minus cosine 30. Okay, clear? So this is how I can calculate the work of my weight. Now, once I calculate the work of the weight, and if I look at my figure, friction and normal will not have any work because they are applied at a fixed point. I apply the principle of work and energy to get omega at state 2. Now, this angular velocity at state 2 will help me into my future analysis because I need to apply now kinetics. So I need to write the 3 equations of motion. Sum of tangential forces equals mag tangential, sum of normal forces equals mag normal, and finally sum of moments about O equals IO alpha. And exactly as we did together, okay, from the last equation we deduce that alpha is 0. Because alpha is 0, no tangential acceleration, so ft is 0. And then we still have to calculate the normal. To calculate the normal, we need to apply n minus w equals mr omega 2 squared. So this is where we use omega 2. So we need to apply the work and energy to be able to compute omega 2 that will allow us to calculate the normal acceleration. And in this way, we have solved for all of our unknowns. Okay? Question on this? Okay. Now, exactly like the case of a particle, we can, in case all forces doing work are conservative, we can or apply the principle of work and energy, or also apply the conservation of mechanical energy. So here you will see that there is a lot of similarity with particle. So, you know, the first conservative force that we are familiar with is the weight. And we have seen that for the case of a particle, how to write the gravitational potential energy? It's plus W times Y of G. If G is above the reference line, we have positive potential gravitational energy. If G is below the datum or reference that we consider, we have negative potential energy. And if you remember, the selection of the datum will not affect at all your final result. Why? Because what we care for is delta y. And delta y will not change if we change the datum. What will just change is the value of Vg, but delta Vg will remain the same. Okay? So the first type of potential energy is gravitational one. And when we have a rigid body, just keep in mind that y is for g. So it's plus mg times y of point g, not y of any point on the body. Now, for the spring, it's exactly the same formula that we have seen for elastic potential energy in chapter 14. It's half k delta L squared. Okay, and whenever, if you want, we have all forces doing work are conservative, we can apply conservation of mechanical energy. If not, we have two options. Or you use principle of work and energy, or you can write that T1 plus V1 plus sum of work of non-conservative forces equals to T2 plus V2. So this is a replacement, if you want, of the work and energy principles. So this also can always work because you consider in this work of non-conservative forces. But what cannot be always applied is conservation of mechanical energy, because when you say conservation of mechanical energy, you consider that there is no forces that are non-conservative. Okay? So nothing new, if you want, here. Whenever all forces doing work are conservative, you have the right to apply conservation of mechanical energy, stating that T1 plus V1 is equal to T2 plus V2. Let us do an example on this. The 10 kilogram rod AB is confined so that its ends move in the horizontal and vertical slots. The spring has a stiffness K equal to 800 Newton per meter and is unstretched when theta is 0 degrees. Determine the angular velocity of rod AB when theta equal to 0, knowing that the rod is released from rest when theta equals to 30 degrees. Okay, so here we can first do the analysis of the system to know if we apply work and energy or conservation of mechanical energy. Of course, work and energy will always work, but conservation of mechanical energy will only work if only forces and moments doing work are conservative. Let us do the analysis of forces. You have the normal reaction on A, but since this normal is applied at a point that is moving perpendicular to the force, the normal force at A will not do any work. You have also the normal force at B, and also it's perpendicular to motion of B, so it will not do any work. We have also the spring force. We know that the spring force is conservative, so we can, it's doing a work, but we can apply conservation of mechanical energy if all other forces doing work are also conservative. And we have the weight. The weight is also a conservative force. So here you have two options: or you apply principle of work and energy, or you apply conservation of mechanical energy. Okay, so let us apply conservation of mechanical energy here. We can write that the kinetic energy at state 1 plus, since we have gravitational and elastic potential energies, so we can say plus V1 gravitational plus V1 elastic. Of course, you can use, instead of V, you can say GPE for gravitational potential energy and EPE for elastic potential energy. Okay, you can, no problem. So plus V1 elastic equals to T2, kinetic energy at state 2, plus V2 gravitational plus V2 elastic. And let us now try to identify the different terms. Okay, always, whenever you have gravitational potential energy variation, you need to consider a certain datum line. And you have the freedom of selecting this reference wherever you want. Okay, so for example, if you want to consider that this position at theta equals 0 correspond to the reference, okay? You know, state 1 is at 30 degrees, so this is position 1, and position 2 is the horizontal one. So if you select the datum at position 2, then V2 gravitational will be 0. And what will be V1 gravitational? The gravitational potential energy at state 1. You are below the datum line, so it's a negative gravitational.
Minus mg8.
Exactly. And you have the angle to be 30 degrees. So this distance is 0.2 sine 30. So we have that V1 gravitational will be equal to minus mg times 0.2 times sine 30. And because they said that the rod is released from rest when theta equals 30 degrees, so you have that T1 is 0. So you will cancel out this term. And they said that the spring is unstretched also in case of theta equals 0 degrees, yani at state 2. So we will cancel out V2 elastic because at state 2, when theta is 0, there is no stretching of my spring. So delta L2 is 0. Okay? So we still have to compute V1 elastic. The only unknown will be the kinetic energy at state 2. Now, concerning V1 elastic, all we have to do is to consider the stretching of the spring. They said that the spring is unstretched at this position. Okay, so we can, if we look at the figure, this distance will represent the stretching of our spring. Okay, so we can say that this distance is equal to what according to the figure? It's 0.4
0.2.
times sine 30. Okay, so V1 elastic can be calculated as half K times delta L2 square. Well, delta L2 is equal to 0.4 times sine 30 square. Okay, and now we just still have to apply the equation for T2. What is T2 in this case, in this problem? What is the type of motion? Who can tell me what is the type of motion here for rod AB?
General.
General plane motion, very good. So we have two methods here. Or we use half mvg square plus half ig omega square. Or what can we use? The second option, half
بنجيب ال IC.
Exactly. Have inertia about IC times omega at state 2 square. Okay. Can you tell me where is the IC here and how we can find the location of the IC?
Perpendicular من A والperpendicular من B.
Yes, very good. So
The
look,
intersection.
if we let us move to the other slide to have a clearer figure. Okay, you have A is moving in the horizontal direction and B is moving in the vertical direction. Here, since the initial position is at 30 degrees and when we release the rod, it will move up. So VB will be upward and VA will be to the, not in this case, to the right, to the left. Okay. And if we draw the perpendicular to get the IC location, we draw the perpendicular to VA, the perpendicular to VB, the intersection point will represent the IC. Okay. So the IC will be located somewhere here. Okay. And now, once we compute the location of the IC, we have that these distances are known. So we have here 0.4 sine 30. Okay. and this is 0.4 cosine 30. We can calculate the distance between G and the IC. Okay, according to our figure, we have angles and we have this distance. So you can easily calculate by geometry. You can say also, since it's a right triangle here, this distance is half of AB. Okay, so the distance from G to IC is equal to half of AB, which is 0.2. Okay, so now all we have to do then is to replace in the equation. So now we can get, as we said, the work of the weight and the work of the spring, or we can talk about V1. We can talk about summation of gravitational and potent elastic energy at state 1 and at state 2 to replace in the principle of work and energy. So now, as we said, 42, you have to approach, or you find the IC and you say it's half inertia about the IC omega square, or you have to apply the general rule. But even if you apply the general rule, how to get VG? You need to find the IC, because what is VG? It's the velocity of its omega times the distance between G and IC square. If you didn't pay attention for this method, you can use also the method of chapter 16, which is to relate velocities of points A and B to find omega. And after you find omega, you can relate the velocity of one of these points to G. So you can use or IC method or vectorial method, both will work. Okay, here they selected the IC method. They said, and they found out that the distance between the IC and G is equal to 0.2. Okay, guys, look, there is a very important, we did a small error. What is the error that we did? Now we got the IC first at which position? When we did the analysis here in the figure. Please, this is very important. You need to pay attention for this. If you do this analysis here, you are getting the IC at position 1. But at position 1, what was the velocity, the angular velocity of your rod? They said it's starting from rest. So in case you have initial angular velocity omega 1, you need to relate velocities at state 1. You get IC at state 1. But initially, they told you the system is released from rest. Okay, so for state 1, no need to get the IC because the angular velocity is 0. You are interested to know about position 2. So please pay attention for what omega you need to find, omega 1 or omega 2. If you want to do the analysis of state 1, you need to find the position of IC at state 1. To get kinetic energy at state 1 is half inertia about IC omega 1 square. But now, since you know that it's released from rest, omega 1 is known, it's 0. You don't care for the position. Since it's at rest, you know IC at this instant, okay? So it's at rest. Now, because you want to have information about omega 2, you need to get the IC at position 2. And at position 2, the IC will be at a different location. You know why? Because if you consider now the second position, which is the horizontal position, what will happen? At the horizontal position, you have that at this position, if we still have VB like this, let's say, B is moving up. So VB here is up and VA is horizontal. If you draw the perpendicular to VA and the perpendicular to VB, they will intersect at A. And since we are interested in position 2, we can say that IC in position 2, okay, IC in position 2 is point A. Okay, so at this position, velocity of point A is 0. That's why A is the IC. And we can say that omega 2, to get VG at state 2, all we have to do is omega at state 2 times the distance from G to IC2, which is point A. So we multiply by GA, which is 0.02. 2 meters. Okay, so we should pay attention whenever we consider, okay, a certain, we should know at which position we are doing the analysis, because the location of the IC might change between a position and the other. Okay. Question
دكتور
on
يعني انت لقيت الاي سي بالبوزيشن 1 عن هيك هايبوثيتيكلي اذا كانوا طالبين اذا ما كانوا قايلين
مظبوط
فروم راست سوري ان
مظبوط.
احنا كثير عم بقطع الانترنت عم بفوت ارجع اقطع على
Yeah,
الميتنج بس مشان
exactly.
هيك
يعني in case
اوكي
ما قالوا لنا
ان كيس
البوزيشن
اوكي
1. in case على البوزيشن 1 ما قالوا لي start from rest, and I want to get the
اوكي
expression of T1 function of omega 1, I use IC at position 1. اتفقنا؟ بس نحن هون, since we have this
اوكي
information, since we know that it's starting from rest, we don't care then to do this analysis. We'll need it only if
اوكي
omega 1 is unknown. If omega 1 is unknown, we need to do it. Okay, but here omega
اوكي
2 is the unknown, so we need to get the IC
yes
at position 2.
we
وعادة
did the
أو omega 1
conservation
أو
لانه النورمال
يعني in
perpendicular
general أو omega 1 unknown أو omega 2 unknown, one of the two. In case
اوكي
omega 1 is the unknown,
اوكي
we use the previous analysis. In case omega 2 is unknown, which is the case here, we use the relation with
اوكي we
IC
did
at position 2.
the conservation of
Yes. Okay. So now, once we related
اوكي
VG2,
we did the conservation لان normal perpendicular معنا غير الويت ولا
مظبوط, ما عندنا غير الwork of weight والwork of spring. Okay. So now, after doing this analysis, we'll be able
deal
to find
thank you
T2 function of omega 2. And then if we apply the conservation of mechanical energy, we have just one unknown, which is omega at state 2, and we'll be able to calculate omega 2. Okay, so also here again we need to combine several chapters, because to find the IC we need to use chapter 60. Okay.
دكتور
Yes,
فيك ترجع على الفيجر
أكيد. Which one?
الأولى تبع الإكسرسايز.
Yes. Yes, رفيق.
هن لو إذا مش قايلين لنا إنه الراد حتبرم وتطلع، بدنا نجيب ال sum of moments ونشوف إذا positive أو negative لنعرف الموشن تبع الراد إذا نزول أو طلوع.
Yes, yes. Exactly.
أوكي وبعد سؤال،
Yeah.
إذا لو كان عنا ال A وال B عندهم ماس، يعني البلوك A والبلوك B عندهم ماس،
Yes.
شو بيزيد على شو بيزيد على
بيزيد
السؤال تبعنا
الكايناتيك انرجي، بيزيد الكايناتيك انرجي تبعهم، ساعتها بناخذهم بقلب السيستم. We take the system block A plus block B plus the rod. So in the kinetic energy computation we need to add plus half MVA1 square plus half MVB1 square at state 1. اوكي. واكيد اذا في فريكشن معهم، يعني اذا مش smooth surface بصير بدك تاخذ الورك of friction applied on A and B، بس هون frictionless surfaces.
وإذا ما في friction يعني ما باخد الرياكشن، أو مبلا لازم اخد رياكشن
باخذ
على
النورمال، بلا باخذ النورمال بس ما بيكون في F، ما بيكون في friction force.
اوكي
اوكي.
اوكي.